All right, we proceed with our afternoon session. It's a great pleasure to introduce Nikolai Saveliev from University of Miami, who is going to tell us about deleted squares of length spaces. Nikolai?
Okay, thank you very much. Let me explain what deleted squares are first. So we'll be dealing with manifolds, closed and smooth. So closed means compact and without boundary, and its deleted square will be denoted by f2 of m, and by definition this is just the square of m, as the name suggests, minus the diagonal. So the way it's called configuration space because it's a configuration space of two distinct points in the manifold m. Okay, and in algebraic topology there has been a conjecture for a while which said that if there are two manifolds which are homotopy equivalent to each other, so this would be homotopy equivalence, then the configuration spaces or deleted squares are also homotopy equivalent. And there had been a fair amount of progress in this conjecture, starting with Leavitt, about 95, who proved that if you put loop spaces on top of the configuration spaces, they will be homotopy equivalent. Okay, then next bit of progress came in the work of Paulina and Klein. That was 2003, and they proved that if you put second suspension in your configuration spaces, they will also become homotopy equivalent. A more recent result due to Raptis and Salvatore. Okay. Let's see. This is 2017. They proved the following: if X is contractible, so X is an arbitrary manifold which happens to be contractible and has more than one point, then you can multiply m by x, and you can multiply n by x, and the two spaces after that become homotopy equivalent. So the key condition, of course, is that X must have more than one point. In other words, its own configuration space is non-empty. Well, you see that things are getting pretty close to the conjecture to actually be true, and it was all fine until in 2004. Longoni and Salvatore again. So it's 2004. They actually disproved the conjecture. The conjecture is false, and their example is about as easy as you can imagine. You take length spaces L71 and L72. And these two guys are known to be homotopy equivalent, but not homeomorphic. And their deleted square or squares or configuration spaces are not homotopy equivalent. Okay, so maybe I should remind briefly what length spaces are. So I'm going to use the standard notation. LPQ will be S3 quotient by the action of the cyclic group of order P, where S3 is the unit sphere in C2 given by the standard equation in complex coordinates. And ZP acts on S3 by also standard formula. It takes ZW to zeta Z, data QW, and zeta is the root of unity. So here we go. Okay, so the conjecture was struck down. By the way, the method they used to prove this conjecture, so they used Massey products. Not on the configuration spaces themselves, but on universal covers. So we know that if length spaces were, if any two spaces were homotopy equivalent, their universal covering space would also be homotopy equivalent. So they proved that universal covering spaces are not homotopy equivalent. So it's a stronger statement actually. And the Massey products, the proof they used was they proved that they vanish for F2 of L71, but not for F2 of L72. And we'll talk about Massey products later, what they are. For now, the big question is, where do we go from here? So we know that length spaces like these two may be homotopy equivalent, but their deleted squares are not. So what's the sufficient condition on what's necessary and sufficient, if you wish, condition on the length spaces for their configuration spaces to be homotopy equivalent? And the conjecture, I'm not sure who stated this conjecture, but it's definitely out there. And the conjecture is that if deleted squares of two length spaces are homotopy equivalent, then the length spaces themselves are homeomorphic. And of course, if length spaces are homeomorphic, then their deleted squares are also homeomorphic. It's a bit of work, but it's true. Then this conjecture would imply that homotopy equivalence of deleted squares would imply that they are actually homeomorphic. So I don't know if this conjecture is true or not, but it will be interesting either way to find out. So what I'm gonna okay, so maybe I should say that there was a thesis by Matthew Miller at Oregon, 2007, a student of Dev Sinha, who calculated the Massey products explicitly for all deleted squares of length spaces. Well, for the sorry, I said universal covers, so I should have put tildes for the universal covers there. So he calculated Massey products for the universal covers, but couldn't compare them. So I guess the idea was, once you know the Massey products for everything, you from the fact that they are equal to each other, you can conclude that length spaces are homeomorphic, and he couldn't do that because massive products turned out to be very complicated and kind of hard to manage. So, and then that's where our work begins with my former graduate student, Kyle Evansley. That was part of his PhD thesis. We pretty much figured out how to compare those Massey products. And we didn't prove the conjecture, but we verified the conjecture for all prime integers p up to 23. The reason for 23 is that 23 is the first prime in which unique factorization fails in the ring of the in the ring of cyclotomic integers. That's due to Kummer, 19th century. So we thought that something may happen at 23. Nothing happened. The conjecture holds for 23 perfectly fine. And what I'm going to talk about is pretty much how is it that we figured out how we compare Massey products. And the method we use is coming from differential geometry. We used the so-called Cheeger Simons Cheeger-Simons differential characters. Okay, so that was kind of introduction. Let's move on and let me explain what Cheeger-Simons differential characters are and how we use them to approach this problem. So let me start with a little motivation maybe. Before there was Cheeger-Simons, there was Chern-Simons. There were Chern-Simons invariants. So what are those? Well, these are defined for 3 manifolds. So M is going to be, for now, closed oriented 3 manifold. And we consider the character variety for M, and that's going to be SU2 character variety. So we are considering all representations of the fundamental group in SU2 and take quotient by conjugation. Then CS, which stands for Chern-Simons, is a function which takes R of M to the quotient of the real numbers by the integers and is given by the formula Chern-Simons of a representation alpha equals 1 over 8 pi squared integral over M of the following differential form. Its trace A wedge dA plus 2/3 A wedge A wedge A, where A is a flat connection, flat SU2 connection. On M, there is only one SU2 bundle over M, a trivial one. So I don't need to specify the bundle whose holonomy is alpha. Okay, so that's the definition of the Chern-Simons invariant. It's well, the issue is that you can replace alpha by a conjugate representation, and Chern-Simons may change, but it only changes by a multiple of by an integer. So this integral changes by a multiple of 8 pi squared, and also you can choose different flat connections representing the same representation, and also the indeterminacy is only up to the integers, so that's why it's quotient by z. Okay, so it has certain naturality properties. One in particular that we need, if you have a smooth map from M prime to M, then you have the commutative diagram. Let's see if I can fit it in here. So you have R of M goes to R over Z, and this one goes via F star. That's the pullback on representations to R of M prime. And then that goes across to R over Z. So these guys are the two Chern-Simons. And over here, you have just multiplication by the degree of the map F. And this is a very nice property, which leads to a non-trivial, just the existence of this property leads to a non-trivial application. Example. Well, I'm not sure who was the first one who came up with this, but I learned about this in the paper by Paul Kirk and Eric Clausen. And they dealt with, among other things, with length spaces. So if you have a length space, LPQ, then every alpha character is given by a representation from the pi1 of LPQ, which happens to be ZP to SU2. They are all reducible representations. So each of them would be conjugate to representation, which sends the generator. Well, this group, by the way, it will be important at some point. This group has a canonical generator, the way we defined it. So it sends that generator to e to the 2 pi I k over p, e to the negative 2 pi I k over p, and 0, and k ranges from 0 through 1 and so on up to p over 2, the integral part of p over 2. And that's kind of obvious. And the less obvious part is the Chern-Simons that they computed. So Chern-Simons for LPQ of this particular representation alpha is given by the formula k squared r over p. That's all modular z, of course. And r is the inverse of q modulo p. So in particular, well, so this is just a calculation, but in particular, if you have two homotopy equivalent length spaces, LPQ and LPQ prime, this naturality property, this diagram, let's see, this is going to be 1 or minus 1 maybe, because it's homotopy equivalence, and this is going to be an isomorphism. And in particular, well, on the fundamental groups, in particular, this is going to be a bijection, and the values of the Chern-Simons, all these guys will be in bijection for two different length spaces. So in particular, we will have that, let's say, for k equals 1, r prime over p up to plus or minus 1 will be equal to k squared r over p. This is modulo integers. And then we keep on rewriting this thing. And with a bit of elementary number theory, we get the conclusion that plus minus q must be equal to k squared q prime modulo p. Okay, so this should look familiar probably, because this is Whitehead theorem. The Whitehead theorem describes what it means for two length spaces to be homotopy equivalent. They are homotopy equivalent if and only if this condition holds. So we proved one direction of the Whitehead theorem by using Chern-Simons. And the other direction is also true. Okay, so you see right away that Chern-Simons functional gives us some non-trivial information about homotopy equivalence. So that was our starting point. We kind of wanted to do something similar using not necessarily Chern-Simons, because Chern-Simons is only defined for 3 manifolds, but we wanted to use it for deleted squares. Okay, and that's where, well, it's kind of funny that we actually defined this invariant ourselves and then realized that it's been discovered way before us by Cheeger and Simons. So here is the story. That was the motivation, now the story. So let X be a topological space. Just arbitrary topological space. Define the Cheeger-Simons flat differential character. So there are some differential characters which are not flat, but ours are the simplest type, flat. So Cheeger-Simons flat differential character. And it's going to be denoted by CS again, sub X. And it's going to be a map now from the character variety of X. So it's the SU2 representations of the fundamental group of X to homomorphisms from H3 of X to R over Z. And the definition goes like this. First, we observe that every class, every homology class in H3 of X is can be realized. It's a Steenrod realization problem, which works in this dimension, in this rank. Every class in H3X is of the form H star of the fundamental class of M for some H, a continuous map from M to X. And M, of course, is a 3-dimensional manifold, closed and oriented, and this is its fundamental class. This is true. And using this, we're defining Chern-Simons, Cheeger-Simons of representation alpha, right? So representation alpha lives in here, right? So this guy will live in here. So to define it, we need to send homology class to R over Z, and the homology class is of the form H star M. Right, and what we do, we take Chern-Simons on M and apply it to the pullback of the representation alpha. So yes, so this is a representation of the fundamental group of M. Well, maybe I should write that alpha is in the represents an element in the character variety. Well, so what do we know about this properties of this invariant? well, it's well defined. Well, the fact that it's well defined follows from calculation in extraordinary homology theories. It's known that the group of oriented cobordisms of X in degree 3 is the same as the third homology of X. This can be proved using Hirzebruch spectral sequence, or there is a geometric proof also. Then, like for the Chern-Simons, we have a naturality property. So that's the second property. If we have a map from X prime to X, well, just continuous map, then we have the following commutative diagram. R of X goes to hom from H3X to R over Z. And over here, we have R of X prime and hom here, X prime, R over Z. And of course, there is the induced map on the right, and there is induced map on the left. And diagram commutes, assuming these are the Cheeger-Simons. Okay, so we would like now to pull out the same trick as we did with the length spaces for deleted squares of length spaces. So for that, we need to calculate, well, at least we need to start by calculating Cheeger-Simons for X equals F2 of LPQ for the configuration spaces. So, well, let's see some basics. Pi n of X is, of course, ZP plus ZP, because we are removing the diagonal of codimension 3, so it doesn't affect the fundamental group. H3 of X is going to be Z plus ZP. Well, that's algebraic topology calculation. In particular, well, and then we need representation. So the fundamental group is this. So we have representation for each factor, and this representation is determined by two integers, k and l modulo p. So I will write it like that. And then here is the answer, calculating the Cheeger-Simons. So for a choice of generators in H3X, well, they are not quite canonical, but they are not too bad. So there is a choice of generators in the homology group. So generator here, generator there, for which Cheeger-Simons of alpha. So on the generator in the copy of Z is equal to k squared plus L squared times R over P. And Cheeger-Simons of on the generator in ZP, and this one is equal to, well, we never bothered to figure out the sign, plus minus 2KL over P. And R is the same as it was before, it's the inverse of Q. So, well, okay, QR is equal to 1 modulo P. So maybe I'll say a few words about computing this, how we compute it. That was the most technical part of the whole work. First, by naturality, enough to compute Cheeger-Simons. of x for x LPQ times LPQ. So there is no need to remove the diagonal. We can work with the closed 6-dimensional manifold. And whatever we compute here will give us the answer for the deleted squares. Okay, so these guys have the same fundamental group. ZP plus ZP. H3 of this X is, maybe I shouldn't call it X, but well, fine. H3X is Z plus Z plus ZP. So there is extra factor. And well, yeah. You know what, let me maybe not call it X after all. Let me call it L cross L for the length space. So pi1 of L cross L and H3 of L cross L. And then let's see, Chern-Simons now, Cheeger-Simons, sorry. For these two guys, we need 3-dimensional representatives, right? These are just coming from the factors in L, so that's easy. The 2Z factors. Give us Cheeger-Simons equals K squared R over P, and for the second factor, it's K squared R, well, L squared R over P. Again, alpha is KL here. And the most interesting part is the torsion, this one. So if we use the standard CW complex structure on the length space, then the generator of ZP is actually this one. You take the product of E1 and E2 and add E2 times E1. So it's a generator, and this is cycle, obviously, but this is a singular cycle. Well, it's quite singular, actually. So what we need to do is represent the same cycle by a smooth manifold, smooth 3-dimensional manifold. So the claim is that this one is represented by H from M to L cross L, and I'm going to tell you what M is. M is obtained by zero done surgery on 2,2P torus link. Well, this is a pretty big theorem. So we had to work pretty hard with low-dimensional topology to get there, but it is what it is. And so the torus link is like this. So this is for P equals 2, and we do zero surgery on it. And lucky for us, this surgery is a Seifert fibered manifold. And well, with parameters, if you wish, they are P1, P -1. So there are 3 singular fibers, whatever that means. It's not important. What's important is for Seifert fibered manifolds, the calculations of Chern-Simons are known. They were done by Dave Oakley in around '94 in his PhD thesis, I believe. And this calculation tells us that for this particular generator in ZP, in the torsion subgroup, Chern-Simons is equal to 2KL over P. So that's basically the idea of our proof. And then now let's see where we are. So we want to use this commutative diagram together with these calculations to get something about a potential homotopy equivalence between x prime and x, where x prime and x are now deleted squares. Okay, so this is just algebra, basically, working with different bases and such. And the result is the following theorem. Of ours. So it's and myself. That's about 6 years ago, 2015. So it's been a while. And here is the claim. Let F2 LPQ prime to L, so sorry, to F2 LPQ be a homotopy equivalence. Then up to permutation of factors in the deleted product, in the deleted squares. So in F2, well, you only need to permute them in one of them. The homomorphism, induced by F on the fundamental groups prime 2 pi 1 F2 LPQ is given by a diagonal matrix. In the standard basis in the fundamental groups. Alpha in the natural basis. Of the fundamental group, ZP plus ZP. And where alpha is, as one might expect, is that factor that makes the two length spaces homotopy equivalent. So, okay. So we learned something about the homomorphism in the induced homomorphism on the fundamental group. It cannot be arbitrary. It has to be given by a diagonal matrix. In particular, we conclude that because of this, we conclude that if there is homotopy equivalence between these spaces, then the length space are homotopy equivalent, well, which is fine. And another observation is that if, that's a remark, if, well, I don't know, I don't want to write it, but essentially if we tried the same trick, not with deleted squares, but with regular squares of length spaces. So length space times itself to length space times itself. If they are homotopy equivalent, what do we know about P and Q prime? It turns out we know nothing. And that's for a good reason, because it's known that LPQ squared is not only homeomorphic, but diffeomorphic for any Q and Q prime. So we know nothing about Q and Q prime when we square length spaces, unless we remove the diagonal. And this is due to Kwasik and Schultz. And Slavik Kwasik was actually the one that we learned about this problem from in the first place. Okay, so now I have still time to tell you about how all of this implies the conjecture, at least in the case of relatively small p. So we are going to combine the above theorem with the Massey products. Pretty much like Longoni and Salvatore told us. So let's see. We have a length space. We do deleted square, and then we do Massey products for the universal cover. So what's the universal cover? Of F2 LPQ. Well, universal cover is denoted by tilde. So this is pretty tame object. Actually, it's obtained from S3 cross S3 by obviously removing the diagonal, but also the whole orbit of diagonals. So what are the diagonals? They are delta k, and there are p of them, and delta k is Z1, W1, Z2, W2. So these are 2 points in the 2 copies of S3, and they are related by the action. One is obtained from the other by the action of the Q, K. So it's W2 for all K from 0 to P minus 1. So, we need to compute the cohomology of this, well, which is pretty easy again, because F2 of LPQ tilde, it projects to S3, and this is a fiber bundle. This fiber S3 minus well, unfortunate notation, sorry. Well, x0, xp minus 1. So the S3 punctured in p points. And this fiber bundle actually has a section, sorry. So cohomology is computed very easily. The answer is H0 of F2 LPQ. Wow, this one is really easy. It's Z, and H2 is P copies of Z, P minus 1 copies of Z, sorry. So with the natural action of Z, P of the cyclic group. So this is the ring of cycloatomic integers. Zeta is still the root of unity. And H3 is also Z, and H5 is also cycloatomic integers. Sorry. And then, so these are the groups, and then the cup products will vanish. Well, simply. Cup products, sorry, on H upper 2, they will vanish for obvious reason. Well, that's the starting point for the Massey products. Once you have vanishing cup products, you can define Massey products, which is like the secondary operation. And it, in this case, it's going to go from H2 times H2 times H2 to H5. So they are all the same ring of cycloatomic integers. And the definition is what it is. Well, for each triple of cycloatomic integers, U, V, and W, we get a cycloatomic integer. But unfortunately, it's only defined modulo an ideal generated by U and W. U and W. And in this case, there isn't much of an ideal since cup products almost all are equal to 0. So you just get a quotient by this for integers A and B. Let me maybe say what Massey products are quickly. So how it works. So we have U, V, and W, which are cohomology classes. We choose co-cycles that represent them. And then since U, V is equal to 0, the cup product, it means that U bar cup V bar is a co-boundary. So it's D of, I don't know, say capital W. And since V and W are 0, then we have V, W equal, it's also a co-boundary of U. And then we define U, V, and W to be the formal, the cohomology class. Of U, of, sorry, the other way around, W cup product W bar plus U bar cup product with U. So this is well-defined modulo the choices of W and U, which cannot be completely eliminated. So that's why we have this extra indeterminacy. Okay, so these are Massey products. As I mentioned, Matthew Miller computed all of them by explicit formulas. The formulas are pretty bad, but they are explicit. And then going back to homotopy equivalences. So if F is a homotopy equivalence, my notations are a little off. So if we have homotopy equivalence of deleted squares, we have homotopy equivalence of universal covers. Then Massey products, they have certain naturality property, which is not strong enough, but it's, so these are Massey products in the Q prime part, and these are the original. And then unfortunately you have to add with integers the pullbacks of U and pullback of W. So this is one. And this has nothing to do with our calculation yet, but our calculation gives us a commutative diagram. And the commutative diagram goes like this. So this is F upper star on the second cohomology. And then we know the action on the fundamental group, right? That's we got from Cheeger Simons. So this is zeta and this is zeta alpha. So that's the extra piece of information. We kind of know that not only that F stars are isomorphisms, but we also know that they are equivariant in this strong sense. And then using these two bullet points, you can go ahead and compare Massey products and see if there is a homotopy equivalence here. So if F is a homotopy equivalence, on the universal covers lifted from homotopy equivalence of deleted squares, we can do algebra using these two, using this and using that, and we arrive at certain conclusions. And unfortunately, the algebra is so awful that we couldn't do it by hand, except in very simple examples. So what we did, we used also do algebra with the Massey products. And to do the algebra, we used computer, and we dropped the cycloatomic integers in favor of the field, cycloatomic field over Z2. And it goes like this. Take any two length spaces, PQ and PQ prime, which are homotopy equivalent. Equivalent, but not homeomorphic. And use the algebra above to check that the above conditions, the two of them, cannot be satisfied. And that's basically how it works. And we've been able to do this for P, for all prime odd prime P's up to 23. Is there a question? Or? Well, so let me maybe show them to show the table of Massey products so you can see what they look like. Let's see, where are they? Here they are. So these are Massey products for L11 too. And instead of zeta, I used T in my table. And the Massey products here, they are like T, let's say T squared, 1 in the middle, and T to the 5th, something like this. You go to the table, this is T squared, this is T to the 5th, and you get the answer is T squared in this case. So this is the table for, and then there are two special polynomials and everything else, well, showing up here and here, and the rest are pretty, and here and here, and the rest are pretty straightforward. So if you look at 11.2 and 11.3, these are two examples which are homotopy equivalent, but whose deleted squares are not homotopy equivalent. You see that the tables are quite different. So it's not really a surprise that we've been able to do these calculations, but to finish this story, I'm still curious if one can actually do algebra better without computer, by hand maybe, and can prove the conjecture in general. The problem, of course, is that we have an algebraic operation with 3 inputs and 1 output, plus certain indeterminacy in the answer. And we also have equivariance condition that we proved. And I really wonder if there is a better way to arrange calculations or arrange algebra, or there is some tool that smarter people would figure out how to handle this. There is a wealth of information in all of this, but we haven't been able to use it to prove the conjecture in general. And I guess I will stop here. Thank you.
Hi, Nikolai, I have a question.
Yes.
Is there, so you talk, if I understand correctly, these are the triple Massey products, right?
Yes. Yes.
So, I mean, I dare to ask you, of course, that's probably even harder. Are there any higher Massey products? Could that be anything interesting there?
Well, we don't have too much homology. I mean, cohomology. They are all pretty much zero. So this, I think, by
So there would be zero.
By dimensional count, everything else must be zero. So that's the only one.
Is there any sort of homotopical structure underlying these triple Massey products? Like, because usually there is some kind of higher categorical structure or something like that that would
that may
code
be
them, I guess.
That's my hope, that somebody smarter than us can find some structure that can be handled more easily than Massey products. I think there should be a way to package all of this.
Yeah, that's right.
Then just say that this follows in two sentences, and that's it. Well, maybe not, but that's my hope. Well, actually, the first approach, maybe I should say this, that our first approach to this problem was using Kontsevich integral, and that didn't work very well, because once you see configuration spaces, there are certain invariants you can extract. And there are invariants extracted by Kuperberg, Thurston, and Leskop. They got, essentially, they got Kassan-Walker invariant that would do the job. But to get Kassan-Walker invariant, they used different configuration spaces. They removed not just the diagonal, but also the coordinate axis. And that was kind of not quite the same problem. There is more homology to work with in that case. But I wouldn't be surprised if there is maybe a way around this problem somehow.